very well-known researcher in two fields. If you're not here, then I have to use this fellow.
This is him, right?
Anyone of them is good.
So. Yeah, I
Cannot see.
How does it sound?
Yeah.
Hello? Yeah. Sharat, can you hear me?
Yeah.
Yeah. So Noga is a very, very famous researcher in two fields, math and computer science. And he seamlessly goes through many areas of both of these fields and has done foundational work in both. In fact, right now he's professor emeritus from math and computer science in Tel Aviv, and is on the faculty currently at Princeton in the math department. And his research spans through many areas, and I'll just read out some of them. It's a subset. Expander graph, de-randomization, algebraic and probabilistic methods in discrete math, information theory, combinatorial geometry, combinatorial number theory, and computational learning, which is going to talk about today. And he has published over 700 papers, and that's a number that I don't care about because I don't count papers. And fortunately, neither does he. He doesn't believe in number of papers, unlike some people who have lots of papers. Okay, which is a great trait to see because he's a real researcher at heart who cares about ideas. So, and in fact, he has many awards, and I wanted to mention them as well. And then I looked at his list of awards, and I see that it is so long that if I start reciting them, there may not be any time left over for the talk. So better if he starts. Thank you.
Okay. Thanks. Thank you, Vijay, for this very nice presentation. I try. The light is somewhat okay. And it's a great pleasure to be here. And let me.
I can't hear you at all at the back. So there's something wrong with the audio.
Okay.
Can you do something about it? Sorry.
Okay.
I can't hear at all.
Sorry. Because this is on. Okay, is it okay now? I can try to speak louder, but tell me, okay, good. So just make a sign at the end there if you don't hear me. So it's a great pleasure to be here. Let me thank Vijay for the invitation, for this very nice introduction, even if exaggerated, and I hope this will not be the only nice part of this lecture. And whenever you give more than one lecture in the same place, and you see that some people who were there yesterday are coming today also, you wonder if the reason is because they enjoyed the lecture yesterday and they want to hear you again, or because the lecture yesterday was so terrible that they want to give you a second chance. But in any case, I want to thank you all for coming. And today I'll speak about PAC learnability of partial concept classes. And most of the new things I'll mention are in joint work with Steve Haneke from Purdue, and with Ron Holtzman and Shai Moran from the Technion. And I'll probably mostly just stand here because I see that if I'm walking then the light is too strong, but okay. So basically this is some attempt to extend the scope of the usual classical PAC learning model of Valiant, and I'll tell you a little bit more about it, so that it will be able to cope with maybe more practical examples. And what I wrote here is that the motivation is that in many practical learning problems, the data satisfies some special properties, and this cannot be captured by the classical model, and these properties make learning easier. And maybe the best example is one of the earliest example of a learning algorithm or learning questions that existed long before people defined even these models of learning. So the perceptron algorithm is from the late 50s. And this is to learn a high-dimensional linear classifier with margin. So we just have some very high-dimensional Euclidean space. It could be infinite dimension if you want, or just high dimension. And we have there a linear function, so just a hyperplane. And we have points that are on one side and points that are on the other side. But we also assume that the points satisfy some margin property. So all the points, let's say, are unit vectors, just to normalize it, and they are somewhat far from the hyperplane. So you don't care much about points that are very close to the hyperplane. So we really want to assume that what we get is points and like a collection of points, and for each point someone tells me if it is above the hyperplane or below the hyperplane. But when it is above or below, then there is some margin. It's not too close to the hyperplane itself. And our objective is to try to learn this hyperplane so that we will be able to classify a new point that is coming. Now this cannot be captured by this traditional theory of PAC learning introduced by Valiant, because in that model, usually you assume that the points that you get come from some product distribution. So you just get some independent, randomly chosen points according to some probability distribution, and we cannot define such a point, such a probability distribution on points that will satisfy the margin property with respect to every hyperplane, right? So if we have some hyperplane, we want the probability to be supported on points that are far from it, and for some other hyperplane, we want it to be supported on some other set of points. So, so this is just one example. You can think about several others. And the question is can we kind of redefine the model so that it will capture this situation? And what we suggested is to do something very simple. And this is just to extend the classical theory by considering what we call partial concept classes. So this means that we would have functions that can be undefined on part of the space. So the space maybe here in this example are points in some Euclidean space, but if our hypothesis is some specific hyperplanes, and for points that are too close to it, this is just undefined. So it means that the function now is not binary, but it is over an alphabet of size 3, which contains also a star. And the star means that there the function is undefined. So this is the definition here. And I have to apologize that there would be quite a few definitions in this lecture, but hopefully I make it not too bad. But feel free to stop me whenever you forget something or whenever something does not make sense. So a total concept class is a class of functions from some set X that can be infinite or finite to 0, 1. So just it gives to every point of X a label which is either 0 or 1. It can correspond, I don't know, the points can be movies, and then every concept which is just a binary vector or a binary function correspond to one user, and then 0 and 1 tell if you like this movie or if you don't like. And as we said, this hyperplanes with margin is another example, and you can think about many others. And a partial concept class is something that looks a little bit more general. So just a class of functions from X now to 0, 1, and star. So on some points of X, the value of the function is star, and that means that it is undefined, and the support of the function is just the inverse image of 0, 1. We look at all the points of X where the value of the function is a binary value. And what is a sample? So a sample is a collection of pairs xi, yi, where each xi is just some point of x, and each yi is a classification of it, so it's either 0 or 1. So this is what we define by a sample. We get a lot of points, and for each point, we know if it is classified as 0 or 1. Here we don't get stars, right? So we just get this. And we call such a sample realizable. I'll talk today, for simplicity, only about what is called the realizable case. There is also what is called the agnostic case when we allow errors, but let's not worry about it for now. So a sample is realizable by some partial concept H if all xi are in the support of this specific concept, little h, and little h classifies every xi correctly. H of xi is equal to yi for every I. Okay, so this is so the first thing we want to know is to try to compare between partial and total concept classes, because one could think naively that maybe partial concept classes do not give you more power, and actually you can do what I'll soon call a disambiguation. So take any partial concept class, change all the stars to zeros or ones in some way, and then look at the total concept class that you get, and kind of try to apply the usual things we know for binary vectors. But we want to show, or we will see, that this is not the case, that really with partial concepts you can do much more. So let me say that a total class, so again, a total class means binary functions or binary vectors, no stars. It disambiguates or strongly disambiguates, let's not worry about the strongly now, it disambiguates a partial class H if whenever we have some partial class little h in capital H, then there is some h prime in this total concept class that disambiguates it, that agrees with h on the support. It just means that h prime is obtained from h by replacing every star by 0 or by 1 in some way. Okay, so this is. So for example, again, if we look at the class of all linear classifiers in RD, so these are just hyperplanes and points that are on one side and points that are on the other side, this disambiguates the partial class of all linear classifiers with margin, where we allow only points that are at least of distance delta from the linear space, and we just don't classify the points that are too close. Okay, so this is like a simple example. And it turns out that one concept that plays a crucial role in computational learning is what is called the VC dimension. So I apologized already that there will be quite a few definitions, but maybe it's natural, so maybe even if you've not seen it before, it will be simple to get it, or definitely at least get the flavor of things. So when we have some subset of the set X of possible examples, we say that it is shattered by a partial or total concept class H. So the concept class is just a collection of vectors or a collection of functions. and we say that a subset Y of X is shattered if on Y we can get every binary possibility. What is written here is that whenever we take some function, any function that we wish f from Y to 0, 1, so only a binary one, then there would be some concept or some function in our concept class H, which could be a class either of partial functions or of total functions, and this H agrees with f on every point of Y. So we want to get all possibilities, and what is called the VC dimension of a partial or total concept class H is the maximum or supremum, if you want, cardinality of a shattered set. So this could be infinity, and it could be finite. And just to see that we understand the definition, I have here some example. So look at the example that we see here. Think about every row as a partial concept, right? So this is a very small set of partial concepts. We have 5 of them. For each row we have 1. The size of X is 4. And you see how each of them classifies every point. And I'm saying that the VC dimension of this is 2. And this is because if you look at the columns 1 and 3, then on them, this set of 2 columns is shattered in the sense that each of the 4 possibilities of 1, 0, 0, 1, 1, 1, and 0, 0, we get them in one of the rows. And this is certainly the maximum, because to shatter a set of size 3, I would need at least 2 cubed, which is 8 distinct rows, and I have only 5 here. Okay, so this is the VC dimension. And the VC dimension plays a crucial role, actually in several, quite a few areas, but also in computational learning. Okay. So here is one theorem that I want to tell you more about later from that paper with Haneke, Holzmann, and Moran. And it really shows that we can express more things with partial concept classes than with total ones. So it says that there is a partial concept class H with VC dimension 1, so very small, VC dimension 1. And whenever you disambiguate it, so no matter how you change the stars into 0 and 1s, then the VC dimension becomes infinity. Okay? And I'm saying, so this actually answers in a strong negative sense some conjecture of Idan Atyas, Aryeh Kontorovich, and Ishai Mansour. And they thought that every partial concept class with VC dimension D has a disambiguation in which the VC dimension is not much bigger. It's just some constant t. And if this would have been the case, then indeed whenever I want to learn, whatever this means, a partial concept class, I would disambiguate it, and then I would use whatever I know for total concept classes, because really the VC dimension being small captures the possibility of learnability. But as I said, this is not the case. And in fact, you see that it fails in the strongest possible way, in the sense that if the VC dimension is 0, right, so that just means that on no single coordinate you see both 0 and 1, because that would already, so it just means that in every coordinate, if you look at the column, you see there are only zeros and possibly stars, or you see only 1s and possibly stars. So if the VC dimension is 0, then in every column you can just disambiguate to the only binary value that appears there, and then you can disambiguate it also with just one binary vector, which would say that the VC dimension stays 0. So if it's 0, then you can disambiguate with 0. If it's 1, you already cannot do better than infinity. So it really fails in the strongest possible way.
Can I ask you
sure.
to understand something? Suppose you take something, a class that has infinite VC dimension,
Okay.
and you leave 2 rows untampered,
Okay.
and put stars everywhere else.
Okay.
So you got a partial class which has VC dimension 1,
That's right, yeah.
and it's
But all the rest would be stars.
and now there is a disambiguation that has infinite.
Yeah, but what I want, you are free to choose a disambiguation. I want something that no matter how you disambiguate, it will be right. So in this,
got it.
yeah, in this example, you just disambiguate everything to be
That's
zero.
why I was
Right.
missing a quantifier.
Okay, sure. Yeah, and indeed, I think I mean, you can try to think about it, and I'll say a little bit more about it. So again, this means that we have this system of vectors of 0, 1 star, if we just want to say it as a combinatorial thing, and it has only very small VC dimensions, so it has only, in this example, only one column on which you see the two possibilities, you don't have even two, but no matter how you change the stars into zeros and ones, then you would have as large a number of columns as you want that is shattered. Okay, this is so we'll say something more about this. This is related to some questions in graph theory and in communication complexity, and it's based on some very nice results of people that I'll mention soon. Now let me say something about learning also, because this is the subject, and again, the trouble is that we need some more definitions, and especially one of them is a little bit technical, so that's the original definition of PAC learnability, but let's try to go over it, and it would not be a disaster even if you haven't seen it before and you don't remember it, because still I think it's possible to understand essentially what it says. So we say that a distribution, so now it's a probability distribution on x times 0, 1, right? So this is a probability distribution on kind of examples and their classification. So this probability distribution is realizable by this partial or total concept class H if for every n with probability 1, if I generate a sample S by choosing n pairs xi, yi according to this distribution, randomly and independently, this P of n is realizable by some partial concept H in H, and the same for total concepts, right? Okay. So this means that the probability distribution is realizable, namely we get this example, and always there will be one function that agrees with all of them. So somehow it's and the prediction error of when you give me some probability distribution P, and I choose some partial or total concept H, so the prediction error is just the probabilities that we get something that H does not classify correctly. Okay, so if we choose H, if it realizes everything, then the prediction error is 0, and if not, then maybe the prediction error is some number. And you see that according to this definition, if this little h of x for some x is defined as star, then this always counts as an error, because we kind of we are correct only if we got the correct binary value, and in our samples always the y is either 0 or 1. So yeah, Milena.
But the learning is always as a function of the distribution P, like in the PAC model.
Okay, sure, yeah, we'll
okay.
soon
I
get to
want
it,
to
right,
clarify.
yeah, sure. So it will, okay. So I still didn't define, but I want to define what it means to learn, indeed. Okay, but what I said is that if H classifies something as star, it's always an error, and therefore if I'm trying to learn something and I try to minimize my probability of error, it is always better for me to classify everything as binary. I don't gain anything by saying that H of some x is star. It's better to me to define it as 0 or as 1, because then, well, in the worst case, I'm still making an error. It will not make things worse. Okay, and this is, so again, the two definitions here. I already went over them. And this is maybe the most complicated definition that will appear here. And this is just the usual definition of PAC learnability. PAC stands for probably approximately correct. And here is what it means. So a partial or total, again, concept class is what is called PAC learnable, is the following calls. So you give me two small parameters, epsilon and delta. One of them will correspond to the probably, and the other one will correspond to the approximately, as we'll soon see. So whenever we have epsilon and delta, then there is some finite integer, n, which is only a function of epsilon and delta. And there is some learning algorithm, A, that is doing A. So what does a learning algorithm have to do? It gets some samples, some classified samples, and then it has to guess a concept that will hopefully also classify correctly some other examples. So again, what we want here, and this is important, that for every distribution P, so it's the same algorithm, but for every distribution P, which is realizable by H now, so we say, so we are free to choose any distribution we want, and then we get a sample of n points generated according to this P, and then the algorithm looks at this sample and does all kinds of things, and we will not worry today about efficiency, although this is also interesting. And what we want is that with probability at least 1 minus delta, the function that the algorithm will generate, so the algorithm generates some function that gives a binary value for every point in X, and then we can ask what is the prediction error of this function that the algorithm generates on this same probability P, and we want it to be at most epsilon. So again, as I said, delta stands for probably, because if delta is small, it means that probably the algorithm, or with high probability, the algorithm generated something H, a concept H, that is approximately correct. The epsilon measures how is approximately correct. And okay, so again, what we want for a class of functions to be PAC learnable, if for every probability distribution that is realizable by something, it's enough to look at finitely many examples that we get according to this distribution, and then be able to predict what we will do for the next examples generated according to the same distribution, and the error will be small. Okay? So this is
polynomially many examples, not finite.
Say that again?
Polynomially many examples.
Yeah, so normally we would want that the number of examples is small, but for the definition we write, I mean, it will turn out actually that it's always polynomial. If so, this is part of the results. If it's finite, it's also efficient, at least in terms of the number of. So this is part of the beautiful theory, but it's just the definition. So it kind of makes sense. I mean, there is this binary or vector of 0, 1, and stars, unknown to us, that we are trying to learn, and we get examples, and then we want, according to the examples, to kind of decide which vector out of our space of possible vectors it is, and we want to make only a small error in probability. Okay. And the fundamental question is which partial concept classes are learnable and how. And let me tell you what is the fundamental theorem of the usual classical PAC learning with no stars, so just binary vectors. So that formally was proven by Blumer, Ehrenfeld, Hausler, and Wormuth, but actually it really appears in an older, implicitly in an older paper by Vapnik and Chervonenkis, which gave their initials to this notion of VC dimension. And it's very nice in the sense that it gives a combinatorial characterization of which concept classes H are learnable and which are not. And the statement is that just such a collection of functions is PAC learnable, if and only if the VC dimension is finite. Okay? And if the VC dimension is finite, then we can ask also, as Milena was suggesting, we can ask how many examples n we need as a function of epsilon and delta and the VC dimension, and the proofs give something pretty good for this, and actually it's in terms of the number of examples, it is efficient. Now note that here we don't care about efficiency. Yeah, but let me also say what is written here because it's important. So what is a learning algorithm? If I don't care about efficiency, well, for the realizable case, it's the simplest thing you can think about. So you just get examples, and what you're allowed is to choose any function that is consistent with all the examples. If it's realizable, then there is such function. Maybe there are many such functions. Just choose any one. As I said, we don't worry at the moment about efficiency, so go over all of them, even if there are infinitely many. Check, find one that is consistent with all the examples that you got. And it looks natural that you can't do better than that, right? Because if something is consistent with all the examples that I got, then it might as well be this vector. So then I just choose it, and I'll classify according to it also all the new x's that will come. And then it's possible to prove that if, and actually if and only if, the VC dimension is bounded, then indeed for the right choice of the parameters, this will be mostly correct with respect to the same distribution. Okay. So we want to do the same for partial concept classes. And here is another result from that paper with Steve, Ron, and Chai. So it says that just as in the case of total concept classes, a partial concept class H is PAC learnable, even only if the VC dimension is finite. However, here the algorithm has to be fundamentally different than the algorithm for the total concept classes. Namely, what you think is a natural algorithm which would maybe output something. So you choose, I mean, we said already that it doesn't make sense to answer, to give as an answer of the algorithm anything that is not binary. Because we never gain something by guessing star. So we have to generate some binary vector. This binary vector does not have necessarily to belong to our set of collection of the space of partial concepts. We can choose any binary vector we want. And something natural is to take some total concept class that disambiguous our partial concept class, and just to choose something from this total concept class that is consistent with everything that we've seen. Again, we know in the realizable case that there would be such a thing, but as I say, something like this actually will fail or can fail miserably. So we have to do something else, and this is also related, so something a little bit weaker and for a little bit different definition was done by Phil Long. Let me not explain exactly the differences. So I want to try to tell you at least some details about the fact that these partial concept classes are significantly more expressive than total concept classes. And as a combinatorial result, this just means that you have a collection of 0, 1 star vectors where the VC dimension is only 1, but no matter how you change the stars to 0 and 1s, the VC dimension becomes infinite, so becomes really large. And this is based on some results in graph theory and in communication complexity by Mika Gus, by Shalev Ben David and Puya Khatami. I'm saying the first names whenever there is a danger of error, because also the brother or father in one of these cases also works in the area, and the others, I don't have to do it, so Tal, Jain, Kotari, and Balodis. And these are very nice results that are connected to some question in graph theory that I want to tell you about, and to some questions in communication complexity. So I'll not say much about it, but I think it's nice. And even if you completely lost me, I'm kind of now starting something else, so you can start listening again if you want. Right? But, okay, so here is a theorem in graph theory by Graham and Pollack. Actually, in their papers, they attribute this specific proof to Witzenhausen. And it says the following. It says that if a graph G is the edge disjoint union of K complete bipartite graphs, then the maximum size of a clique of it is at most K plus 1. Equivalently, and actually this is how it is formulated in their paper, if you have a clique, just a complete graph on K plus 1 vertices, and you try to partition the edges, so to partition them into pairwise edges shown complete bipartite graphs, then you need at least K of them. And you can do it with K of them in many ways, for example, by stars or by in many ways, okay? And one reason that this theorem, people like it, well, I like it, is that it has very short proofs, quite a few short proofs, and but all of them use linear algebra. So basically, there is no proof that is purely combinatorial, but really different. So you can use some dimension arguments, some linear systems, some eigenvalue arguments. So there are very different proofs, but all of them use linear algebra, including actually a paper by Vishwanathan, in which the title is a counting proof of the Graham-Pollack theorem, but the title is misleading. And really the counting argument kind of replaces, you really prove the linear algebra thing you need by some sort of counting. But let me, okay, so this is a nice theorem. And sometime quite long ago with Mike Sachs and Paul Seymour, we were wondering about the maximum possible chromatic number of such a graph. So suppose we have, again, a graph, which is the edge disjoint union of K complete bipartite graph. So we said that the clique number of it can be at most K plus 1. Can the chromatic number be bigger? Maybe also the maximum possible chromatic number is also K plus 1. That would be very nice. So again, maybe... yeah, and I should say that because of some connection of these two communication complexities that I'll not explain, we realized with Ishai Chaviv, and the same was observed by Mubai and Vishwanathan, that this maximum chromatic number is at least not very, very big, so it's not more than something like K raised to the power log K. Well, still much, much bigger than K plus 1, but okay. And we were wondering about this. So, it's often, it's nice to prove nice theorems, but sometimes it's better to ask a good question or to raise a good conjecture. And the only thing that is even better is to raise a wrong conjecture. And so again, let me specify it here. So our question, or if you want to formulate it as a conjecture, is it true that the chromatic number of a graph, which is the edge disjoint union of K complete bipartite graphs, is it at most K plus 1? Okay, so the first who showed that this is false were Huang and Sudakov, and they constructed such graphs with chromatic number at least some constant K to the 6/5. So definitely bigger than K plus 1. Then an even bigger no, and this was maybe the main breakthrough, was done by Mika Gus, and he showed that there are such graphs with chromatic number at least more than polynomial in K. So K raised to the power some fractional power of log K. Okay? And then there were several improvements based on similar ideas, and the final word is in a few papers actually by Balodis, Shalev Ben David, Gus, Jane, and Kothari. And that's an even bigger no, and it's almost tight in the sense, so I told you that K to the log K is an upper bound, and really there are such graphs with chromatic number at least K raised to the power log K to the 0.999, let's say. Okay, so it's almost K to the log K. And the proof is not very complicated, but it's kind of a series of reductions that go through communication complexity, go through some technique called lifting, and go back to combinatorics. And so it's kind of really very nice, and it's not so easy to see what are these graphs. But so we get that they exist, but okay. And what I want is to try to show you why this is relevant to the question about disambiguation, namely of the existence of partial concept classes with VC dimension 1, so that any disambiguation gets a very big VC dimension. Okay, so that's another reduction, and that's pretty simple, so I'll try to show it. Of course, nothing is really simple after you talk 45 minutes, but somehow I'll try to at least explain the flavor of things or give you enough details to get the impression that if I would have had 10 more minutes, I could have convinced you that with 30 more minutes, I would have been able to show it. So really, it's a simple proof, but let's say, okay. So let's see. So suppose we have a graph G, which is the edge-disjoint union of K complete bipartite graphs. And we want to somehow connect it to vectors of zeros, one, and stars. So what we can do is we can look at a matrix where the rows are indexed by the vertices and the columns are indexed by these complete bipartite graphs. Okay? And in place AVI, corresponding to vertex V and complete bipartite graph number I put 1 if this vertex belongs to the right vertex class of this complete bipartite graph. I put 0 if it belongs to the left vertex class. And I put star if it is not one of the vertices of this complete bipartite graph, right? So I had here some example where you see a graph and you see a coloring of the edges of it by complete bipartite graphs. And for example, if you want to look at the column corresponding to the red complete bipartite graph, this is this first column, and the vertices are labeled here 1, 2, 3, 4. So you see that the only vertex here, so maybe 1, 2, 3, 4. So the only vertex here that is in the bottom vertex class of the red graph gets 0. The 2 vertices that are in the top vertex class get 1, and the 1 vertex that does not belong to the red gets a star. Okay, so this is a way to get a matrix of 0, 1 star from such a collection of complete bipartite graphs that give me a graph. And then there are 2 observations, both of them very simple. So the first fact is that if we look now at the partial concept class that just correspond to the rows of this matrix, okay, then the claim is that the VC dimension of it is at most 1. In fact, on any 2 columns here, you cannot see more than 2 distinct binary projections. Not only can't we have 4, we can't have more than 2. And the reason for it is very simple. So didn't write it here because, yeah, it's written here that if you have two columns, so the two columns correspond to two complete bipartite graphs, right? And if you have two columns in which in one row correspond to one vertex, you see, for example, 0, 1, and in the other row corresponding to another vertex, you see 1, 0, then it means that the edge between U and V is covered twice, is covered in both of these complete bipartite graphs because it's 1 versus 0 in both of them. So we cannot have on two columns here, we would never see 1, 0 and 0, 1, and also we would never see 0, 0 and 1, 1. Okay, so it just, so the VC dimension is 1. Now also there is some simple connection to coloring. And the claim is that there is a disambiguation of this class, namely I can change these stars here to zeros and ones and get Q distinct vectors, only Q distinct binary vectors, even only if the chromatic number is at most Q. And again, the reason for this is very simple, and it's written here. So if you look at a set of rows that can be disambiguated to the same total concept, to the same binary vector, like these two red rows that you see here, so they must correspond to an independent set in the graph. Here it corresponds to these two vertices that are not connected. And this is because if two vertices are connected, then one of the bipartite graphs will cover them, and therefore they will have 0 versus 1, and we will not be able to disambiguate it. So as I said, I know that, that again, after 45 or 50 minutes, it's hard to follow even a simple argument, but definitely it's easy to see that it's easy, right? That there is nothing complicated here. So it means that once we have these two facts, then if we take this example of Balodis, Ben David, Gus, Jane, and Kotari, it means that there is a partial concept class H sub k, let's say, with VC dimension 1, right? Because we said that in those examples we get VC dimension 1, and it consists of vectors of length k. It corresponds to k complete bipartite graphs that are pairwise edges joined, so that in any disambiguation, the number of distinct vectors that we'll get in this binary vectors that we get in the disambiguation will be at least a chromatic number, namely it will be k, almost k to the log k. Okay? And then we need another basic fact that is often used in this VC theory, and that's an old lemma of Sauer, of Perlis and Schellach. Actually, some version was proved already by Vapnik and Chervenet too. And this just says that if we have many binary vectors of length k, then the VC dimension is big. Okay, so just, and basically if you have that many, k to the log k to the 1 minus little 1, then it means that the VC dimension, there is a shattered set of size at least log k to the 1 minus little 1, and this gives us a space of partial concepts with VC dimension 1, that whenever we disambiguate it, the VC dimension must become large, and we want it to be infinity, so we really take just a disjoint union of these examples hk for a growing sequence of k. So it will be right. So this basically it, and it's yeah. So it's simple given the known results, but it's quite intriguing. I want to say very quickly some. So first, I wrote here that this bound for the number of vectors that you get in the disambiguation is essentially tight, and this is another result that is proved by some sort of a version of an online learning algorithm, but let me not talk about that. So it just there is some proof that is written here that will not go over it. because I want to say a few words about learning. Okay? And again, I'll not say much. So we said that even when we have this family of partial concept classes, it's still true that it is learnable according to this definition that maybe technically is hard to remember, but it basically says that if you see enough examples, then you can guess the next ones and be mostly correct. So something is learnable even only if the VC dimension is finite, but the learning algorithm should be more complicated. In the proof of the positive side follows some approach of Hausler, Littleton, and Wormuth for total classes. And maybe I'll just say something quickly. Yeah. Maybe I'll not. Yeah, I want to try to finish in time. So let me just say that it uses some other algorithm, so not the natural one, and it uses some way of orienting some naturally defined graph and kind of guessing according to this orientation. So this is something that works, and there is something maybe interesting here, but I'll not talk about it. And let me say again just 2 words about the impossibility result, so the fact that we really have to apply different algorithm and cannot do the natural one. So this again follows from this example of this partial concept class with VC dimension 1, which actually we can add to it even the all 0 vector, and still the VC dimension will be 1, because we said that in this example, on every 2 coordinates, you have only 2 out of the 4 possible projections. So even if you add the all 0 vector, is still, when you disambiguate it, you will get infinite VC dimension. And that means that we have this partial concept class with VC dimension 1 that contains arbitrarily big shattered sets. Okay, so we have these bigger and bigger sets on which we see all the possible binary projections, and then we can somehow think that if we would choose some, so we want to claim that for any finite m, that this is not learnable by the usual thing. So for any finite m, there is some partial concept and a probability distribution p on the inputs and a rule to choose one of those possible binary vectors that are consistent with everything we've seen, that will be consistent with all what we've seen, but will still be wrong with probability 0.999. So this really follows from the fact that there are these arbitrarily large shattered sets, and if we just define the rule in an appropriate way, we can see that this happens. So I apologize. I mean, I know that it's pretty hard to. I mean, you are not supposed to follow the details here, but hopefully you can believe that this is true. Let me just finish by telling you something about. So, you know, normally in a lecture there are 3 parts. You kind of start by the introduction, where you say what you are going to talk about. Then you actually talk about what these things that you are talking about. And at the end you summarize and you talk about what you talked about. But sometimes there is a 4th part, and this is where you talk about what you are not talking about. And this is what I want to do for a minute now, because there are quite a few topics that I didn't cover. So really the paper that we had is pretty long, and the title was a theory of PAC learnability of partial concept classes. And what we tried is to follow through basically everything that has been done for this usual model of PAC learning and to see what happens for partial concept classes. But I knew that here I'll not have time to cover everything, so I was more modest in the title also. I didn't say a theory of, but let me just say the relevant buzzwords that I didn't cover. So there are sample bounds. You can ask how many examples you have to see, and one can get pretty tight sample bounds, both upper and lower bounds, as a function of the VC dimension and epsilon and delta. Then there is this characterization of agnostic learnability. I was talking only about the case of realizable. We don't allow errors, but you can allow errors. And again, it's basically the same characterization. Something is agnostically learnable, whatever this means, if and only if the VC dimension is finite. And again, the sample bounds would be similar. Then there is something called compression schemes. Let me just say the buzzwords. And here, partial concepts behave very, very differently than total concepts. There is something called little song dimension in its relation to online learning. And again, here it behaves similar to the case of total concept classes. There is connection between little song dimensions, something called threshold dimensions that behaves very differently. So this is just to say that in some, on some results they behave differently for partial concepts and some behave the same. And then there is a connection to private learning where we really don't know. There are some interesting questions there. And let me only mention one problem of the two. So suppose we look at this partial concept class of linear classifiers with margin delta. That's the one I started with. So X is a set of all points of norm 1, let's say, in some Hilbert space of infinite dimension, if you want, or of a very big dimension. And we have this function H that is classifying the points, all the points that are of margin, at least gamma. It classifies it according to the order, and it gives a star for all the ones that are too close. So this one, it's not too difficult to show, and this actually follows from the perceptron algorithm, from some classical results on learning linear classifiers, that the VC dimension of this partial concept class, independent of the dimension of the Hilbert space, is bounded by a function of this delta. It's not more than some constant over delta square. And it will be interesting to know if this admits a disambiguation with finite VC dimension. So we had this example, but it's a very unnatural example of something with VC dimension 1, that whenever you disambiguate it, the VC dimension becomes very large, or infinity. But here is some very specific example where we really don't know how to or if it is possible to disambiguate it. And it might be the case that that disambiguating it will necessarily make the VC dimension very big. There is some a paper in the coming Stock conference that that kind of says something relevant, but does not quite answer this question. And let me just apologize for going a little bit over time, and thank you for your patience. Yeah.
A lot of people do ML here.
Okay, yeah, it's hard.
Okay, so we thank Noga again,
Okay.
and
Thank you.
yeah, for coming all the way.
Thanks. Yeah.
So for students who come here for the code, the code is a PAC